Here is some from 2.5, the implicit. First thing I did was I divided by 4, and that made xy equaling 9/4. Then I did a product rule, solved for dy dx, and plugged it into point slope over here to get the slope, the equation of the tangent line. Now 43 is the same instruction, so I'm still going to do y minus the y value equals m times x minus the x value. So, y minus x minus, what goes in place of the y value? 0, and in place of the x value? 1. The only thing I need is the slope, right? And if the slope happened to be a 1, what would be my equation? Now, how would I get the slope to be 1 would be finding dy dx, right? So let's do that. Take the derivative here, dx dx, which happens to be 1, plus the derivative of y, which is dy dx, minus the derivative of a constant, which is 0. If you do the derivative of natural log of u, its derivative would be u prime over u. U is x squared plus y squared. That's what the u is. Now u prime is its derivative. So term by term would be 2x dx dx plus 2y dy dx. So what does that make this now? I have 1 plus dy dx equaling 2x plus 2y dy dx all over x squared plus y squared. Instead of trying to solve for dy dx, I'm just going to substitute in my values because I might make a mistake in isolating the dy dx. So instead of making that mistake, I think I'm going to substitute in right now. What is the x value? 1. So I put 1 here and a 1 here. What's the y value? 0. Notice that whole thing goes away now. So I have 1 plus dy dx equals 2, which means dy dx, or the slope, is 1. So I put a 1 in for that slope, and I get this equation. Okay, 49 wants a second derivative. The second derivative is usually written d2y, because the 2's with the d, because it's the second derivative. dx2, and this time the 2's on the x because you took the derivative both times with respect to x. So we take the derivative of the left, 2x power base, 1 less power derivative of base. Because it's an x, you write dx dx. Power base, 1 less power derivative of base. Because you're taking the derivative of y, you write dy dx. And the derivative of a constant such as 4 is 0. So I would subtract the 2x, and then I would divide by 2y. And I would find out that the dy dx is negative x over y. Now that's not the second derivative, but it is the first derivative. To get to the second derivative, you have to take the derivative of the derivative. So we've done the first part. Okay, when I go from the first derivative to the second derivative, I have to take the derivative of this first derivative. I try to teach you best practices, so I'm going to keep the negative out as a constant factor. That way I don't have to confuse myself on the inside of the quotient rule. I'm taking the derivative of a quotient, so I have to use the quotient rule. The bottom times the derivative of the top, which is dx dx, minus the top times the derivative of the bottom, which is dy dx, all over the bottom squared. So that gives me a negative, that's a y minus x times dy dx all over y squared. At this point, I'm going to replace dy dx with what it says dy dx is. Negative x over y. So what happens here? I'll keep my negative out, and I have what? I have y. Would that become plus x squared over y all over y squared?
Yeah.
I won't take a fraction and a fraction, so the opposite of dividing by y is to multiply by y, but I'm going to multiply by a fancy form of 1, y over y. Y times y is y squared. Multiply here, the y's cancel, leaves you plus x squared. On the bottom, y squared times y to the first is y to the third. Many times the second derivative has the disguised form of the original in it. So you may notice that x squared plus y squared is equivalent to what? 4. And there is a negative in front of this whole thing. So the answer they're going to have is negative 4 over y to the third. Again, that's the second derivative for this.